Hello, welcome to module 1 lecture 3 of the course VLSI design verification and test. In this module we will take a deeper look into the scheduling of operations within a basic block in high level synthesis. So, before going into the scheduling, a bit of a background. How have we come to this place? So, firstly we said that the application will be defined in terms of a high level language, high level hardware description language like Verilog, and describing its behavior. Now, after we have obtained this Verilog code, each module of this Verilog code will be parsed and the flow chart from this module will be extracted. Now, corresponding to this flow chart, we will be able to obtain a control flow graph of the module. So, what will the control flow graph show? The control flow graph will show how the control flows through various paths in the module. So, there would be various mutually exclusive tasks or operations that will be conducted, and the control will decide which mutually exclusive sets of operations will be chosen and which will be not based on data input. So, now how does a control flow graph look like? A control flow graph, in a control flow graph, the nodes are basic blocks, as we said before. A basic block is a piece of sequential or straight line code with a single entry point and single exit point. Control cannot come into in the middle of the basic block, and control also cannot go out of the basic block in the middle. So, control comes at the beginning of the first statement of the basic block and goes out at the end of the basic block. So, and the edges, what do they denote? They denote the dependency among the basic blocks. Now, we also said that given this control flow graph with basic blocks and their dependencies, I can directly generate the master controller. So, what will the master controller control? The master controller will control when will the operations in a basic block be initiated, right. However, as we also said before, that the complete master controller cannot be generated at this step, because the complete master controller will be a tool that will allow us to ascribe timing information to each operation in a hardware synthesized circuit. However, until we have not ascribed explicit timing information to each operation within a basic block, we cannot ascribe the complete timing information of the module. So, therefore, to obtain the complete master controller, we need to ascribe timing within a basic block, timing to operations within a basic block, and timing to operations within a basic block is done through scheduling. So, next we have now arrived within a basic block, and we have to schedule operations within a basic block. Now, before going into scheduling, we also said this before that all operations within a basic block can ideally be scheduled in a single clock cycle. However, if we do so, then there will be unacceptable hardware cost and delays. So, how can all operations be done in a single clock cycle? Because there are no mutually exclusive operations within a basic block. All operations are performed. It is simply a data flow graph showing the dependency of the data. So, data comes in, gets transformed through operations and goes out at the end of the basic block. There are no control operations in it, there are no mutually exclusive operations in it. So, however, the length of the clock cycle has to be at least equal to the propagation, the total propagation delay in the critical path. So, what do we mean by this? So, each of the operations, say this one, this one, this one, each of them has a propagation delay, because it has to be executed through a resource. And what is a critical path? critical path is the highest weighted path from the source to sink inside a basic block. For example, this path has has 3 operations, this plus this plus this. So, this is a critical path. Now, the clock cycle has to be at least big enough so that all 3 operations can be performed in sequence through this basic block, right. And therefore, because this clock will also feed to other operations other throughout the circuit at different places. So, this clock cycle, although is sufficient for this basic block, may cause unnecessary delay in other basic blocks. Where let us say in that basic block I have 2 sequential operations like this and this, I do not have the third. So, therefore, it will perform these 2 operations and wait, because the length of the clock cycle is such that 3 sequential operations can be executed. So, the clock cycle length has to be judiciously decided and adjusted according to the circuit that we have, according to the need that we have. Now, why did we say all this? Because then we need to ascribe timing. If we do not do everything in one clock cycle, we need to do different operations in different clock cycles. So, therefore, ascribing such operation as to different clock cycles is the very problem of scheduling. Ascribing the timing information to each operation within a basic block is the problem of scheduling. So, what does scheduling do? It assigns a start time to each operation in a basic block, and the controller it allows the generation of the controller, so that those operations can be directed at as those time steps within the basic block. Now, choosing a time step for each operation in a basic block is basically an optimization problem, as we will see in depth in the next 2 classes. The time step is also called a control step or a C step. So, scheduling is the task of assigning a time step to each operation in the data flow graph or the operation constraints graph. However, choosing a time step for each operation in general is not a trivial problem. It's generally an NP complete optimization problem, as we will look inside in depth. And depending on the performance of a schedule, the performance or how good the schedule is can be characterized through various attributes. For example, the number of time steps that the schedule took to assign time steps to all operations. So, the lower the number of time steps within which all operations in the basic block can be scheduled, better is it in terms of performance of the circuit, faster will be that circuit. However, in general, to perform in a lower number of time steps requires higher resources, more resources, as we will also see. So, the next attribute is how much resources were consumed by this schedule, and other attributes could be how many temporary registers were required, muxes, demuxes, etc., as we will see. So, depending on the type of scheduling that we are doing, depending on the number of resources that we have, the amount of time that we are taking to schedule, there are principally 4 different kinds of scheduling problems that are there. Literature says there are 4 different kinds of scheduling problems within a basic block. The first one being resource unconstrained scheduling, where we have no constraints on the amount of resources that we can use. The second one is time unconstrained scheduling, where performance is not an important factor. We want to take as low resources as possible, and delay is not a matter to us. So typically such circuits or such chips we would like them to be very small in size. That is why we want to have a critical view on the resource consumed and not so on time. So the next two cases are more generalized scheduling problems, resource constraint scheduling and time constraint scheduling. We will look at each of them one by one. So before going into the scheduling problem, we will take a general example. This running example we will be using throughout the topic of scheduling that we will be dealing with. So on the left of the screen we have a basic block. So this can be assumed to be the hardware description in Verilog, a behavioral description of a basic block. So x1 equals to x plus dx, u1 equals to u minus 3x u minus 3x u dx minus 3y dx, y1 equals to y plus u into dx, and the last one c equals to x less than a. Now the corresponding data flow graph of this basic block is shown on the right of this slide. So see, the operation 1 takes as input two independent variables 3 and x. Operation 2 takes two independent variables u and dx. So operation 3 performs the operation 3 into x into u into dx, and operation 6, for example, performs the operation 3 into y. Operation 7 performs the operation 3 into y into dx, and then here operation 4 performs u minus 3 into x into u into dx, and in 5 we obtain the final u1. Similarly, we obtain the y1 and c variables as outputs of 9 and 11 operation, the operation number 9 and operation number 11 respectively. Now given this data flow graph, we have to obtain the operation constraints graph. So this the data flow graph that we obtained in the last slide is shown on the left hand side of the slide, and the corresponding operation constraints graph is shown on the right side. Here the independent variables have been removed. We have made the graph polar, having a single source node and a single sink node, and we have only shown the dependencies among the operations, right. So in this way we have obtained the operations constraint graph. So this operation constraints graph basically we will be using throughout the topic of scheduling. So the first type of scheduling that we had said was resource unconstrained scheduling. So the definition is the problem definition is this: schedule operations within a basic block such that all operations can be performed in correct sequence in minimal time using unlimited hardware resources. So there is no limitation on the hardware resources that we have. Hence the solution approach is to just topologically sort the operations constraint graph that we have and label the nodes in topological order. So this topological order will give me the schedule, because finally we just have to assign a distinct C step to each level that we have obtained in the after topological ordering of the graph. So such an approach has been adopted in the SHAP algorithm. So it's generated from the DAG or operation constraint graph by a breadth first search from data sources to sinks. So how does it operate? It starts with the highest node that have no parents, the independent nodes in the DAG. So all independent nodes are scheduled in level 1, and then time steps are assigned in increasing order as we proceed downwards. So, after we have scheduled the independent operations, a few more nodes become independent and ready for scheduling, and they are scheduled, and we perform as many nodes, as many ready nodes are there, we schedule all the ready nodes that are available at a particular time step to that step. So, it follows the simple rule that a successor node can execute only after its parent has executed. So, an example, the operation constraint graph that we obtained is shown in the left, and on the right we have the corresponding ASAP schedule. See that all the independent operations, this and this have been scheduled in step 1, and then after these have been scheduled, then 3 becomes ready, 7 becomes ready, 9 becomes ready, 11 becomes ready, and they are all scheduled in step 2. After they have been scheduled, after 3 has been scheduled, 4 can be scheduled. So, 4 is executed in time step 3. 5 can be scheduled after 4 has been scheduled. So, 5 has been scheduled in time step 4, right. So, we will therefore get a very fast performing basic block if we do an ASAP schedule, but obviously we need unlimited hardware. For example, in step 1 we require 4 multiplication operations, and if we had a multiplier that will perform these performing these operations, we need 4 multipliers, because 4 multiplication operations are being performed concurrently in step 1, and hence the area of the obtained circuit will be high. Now, a similar algorithm is the ALAP algorithm. How is it different from ASAP? ASAP has been obtained from as soon as possible schedule. ALAP on the ALAP correspondingly has the name as late as possible, right. It works very similar to the ASAP algorithm, except that it starts at the bottom of the DAG and proceeds upwards. ALAP solves the latency constraint problem, and the latency bound we can give any latency bound that is suitable to us. Obviously, we can give the latency bound that has been computed by the ASAP algorithm. For example, in the previous ASAP schedule we had obtained a latency bound of 4. So, if we use the same latency bound 4 and apply it to the ALAP algorithm, we will obtain something like this. On the left hand side, again the operation constraint, the unscheduled operation constraints graph has been shown. On the right side we obtain the ALAP schedule. So, ALAP schedule, as we said, the ASAP schedule starts from the source towards the sink, ALAP schedule progresses from the sink towards the source. So, the NOP has been scheduled, the start of the NOP operation is at time step 5. So, all operations on which NOP depends can be scheduled in the previous time step at time step 4. So, NOP depends on operations 5, 9 and 11. So, these 3 operations have been scheduled in time step 4. At time step 3, all operations on which 5, 9, 11 depends can be scheduled. So, 4, 8 and 10 has been scheduled in time step 3. In time step 2, 3 and 7 has been scheduled similarly, and in time step 1, 1, 2 and 6 has been scheduled. So, this is what is the ALAP algorithm. Now, from the ASAP and ALAP algorithm, a few very important concepts can be obtained, and these concepts are applied in the more generalized scheduling problems that we will take up in due course in the next few slides. So, mobility is defined for each operation. What is mobility? Mobility is the difference between the ALAP time and the ASAP time of a schedule. And what does it provide? This difference between ALAP and ASAP provides a measure of the slack that is available on the start time. So, this mobility, this term mobility is also called the degree of freedom of an operation node, because it defines the number of cycles by which an operation can be moved upwards or downwards in the schedule. So, taking an example, in the same operation constraints graph that we have, we see that those in the red lines, the red line in the right side here, this one represents the critical path, because all nodes in this path has 0 mobility. Hence, V1, V2, V3, V4, V5 all have 0 mobility. Operation, see now that operation 6 and 7 has mobility 1. Why? Operation 6 can be scheduled in either time step 1 or time step 2. Similarly, operation 7 can either be scheduled in time step 2 or time step 3 with the latency bound of 4 that we have. So, the mobility of the operations 6 and 7 becomes 1. Similarly, the 4 operations 8, 9, 10, 11 has a mobility of 2. Why? Because it is easy to see 8 can be scheduled in operation in time step 1, 2 or 3, 9 can correspondingly be scheduled in time steps 2, 3 or 4, 10 can be scheduled in time steps either in 1, 2 or 3, and 11 similarly can be scheduled in time steps 2, 3 or 4. Okay. So, with this concept we now move into time unconstrained scheduling. From resource unconstrained scheduling, now we move to time unconstrained scheduling. So, what is the problem definition of this scheduling? Schedule operations within a basic block such that all operations can be performed in correct sequence using minimal hardware resources in unlimited time. So, as we said, we now have unlimited time, there is no bound on performance. Performance can be as bad as possible. However, we need to consume as low amount of resource as is possible. So, how do you do that? Perform a serialized topological sorting of the DAG and assign a C step to each operation, so that optimal scheduling may be performed. Right. So, we will not look into this scheduling, as this it is easy to understand what we do here. We just perform a serialized topological sort and schedule the DAG, and therefore, we will not look at this anymore. Now, we move into the more generalized scheduling strategies. So, the first one here is resource constrained scheduling. So, what is the definition of the problem? Schedule all operations within a basic block such that they can be performed in correct sequence in minimal time given the available numbers and types of resources. So, now we have a constraint on the total amount of resources that we can use. Now, given this constraint on the availability of resources, we have to perform all the operations in the basic block in minimum time, right. So, we want to maximize performance given an area constraint or a resource constraint on the circuit. So, moving on, in this type of scheduling, we will be given this operation constraints graph, and we will have different symbols to represent a few things. Firstly, n represents the number of operations in the operation constraints graph, the total number of operations that are there. Nr represents the number of resource types available. Ak equals to the upper bound on the number of resources of type k. So, suppose you have both multiplication and addition operations within an arbitrary or basic block, right. Now, additions must be performed using a separate adder functional unit or resource, and multiplications will be performed by a multiplier resource. Now, let us say we have 3 multiplier resources and 4 adders. So, A k, where A multiplier will be 4 because we have 4 multipliers, and let us say 3 adders. So, A adder will be 3 because we have 3 adders, and NR will be 2 because we have 2 types of resources, one is adder and one is multiplier. Ti will represent the start time of each operation Vi. So, the operation constraints graph is represented by G equals to V comma E, the nodes being defined as Vi, and the start time of a node will be defined as Ti. TIS is the ASAP time of Vi. So, when we have done the ASAP schedule, we have labeled each operation with its ASAP time, its ASAP schedule time. So, that ASAP schedule time will be designated as TIS. Similarly, TIL will designate the ALAP time of operation. So, there is a mistake here, it is represented as ASAP, but it will be ALAP time of operation Vi. And Di denotes the propagation delay corresponding to operation Vi. So, the propagation delay will mean how much time it takes to perform, let us say, an addition on the adder circuit, on the adder resource that we have, that is the propagation delay Di. Now, given these notations, we will look at how difficult this problem of scheduling is. For example, we actually have polynomial time optimal solutions in a very stringent few cases. For example, only when the number of types of resources are just one, we have all addition operations within the whole basic block, within the full DAG. All operations take the same delay or same propagation delay. All operations have the same propagation delay, unit propagation delay, and the DAG is basically a tree and is not a DAG as such. For example, when does a DAG become a tree? When removing the direction constraint of the DAG, even after removing the direction constraint of the DAG, there is no cycle in the DAG, then the DAG becomes a tree. So, it has been shown that if we have these constraints, then a polynomial time solution or a linear time solution can be obtained for such an operation constraints graph, and that is basically obtained through the Hughes algorithm. However, if the DAG is generalized, I have not written down here, if the DAG is generalized, then we can have at most two resources. We can have at most two resources in a generalized DAG of one type, and then only we can obtain polynomial time solutions. More than two resources, 3, 4, 5, but a constrained number of resources, we don't know, we still don't know whether we get a polynomial time solution or not. So, basically what we take in general is that the solution is NP complete if the number of resources is greater than 2 and we have a generalized DAG. So, the problem is as complicated as this. So, hence if the problem is complicated, and which means that the problem is NP complete, then we have different types of strategies to solve it. The optimal solutions can be obtained by various mechanisms. For example, we can formulate the whole problem as a linear program, as an ILP, and then we have solving tools, ILP solving tools to solve such ILPs and get the solution. We can apply advanced state space search techniques such as depth first branch and bound and best first branch and bound to exhaustively but systematically search the whole state space and find out an optimal solution, where the state space would mean all the different possibilities for assigning operations at different time steps to different resources resources and by exhaustively searching through all the possibilities find the best solution that we get. However, why we said that even if it is even though it is exhaustive, the by systematically searching the whole state space, we can prune or cut off some parts of the state space and get away by not searching them, because through such systematic technique we can ensure that that portion of the state space will never contain the optimal solution. We will look at these optimal solutions in a bit more detail in the next lecture. Now, along with optimal solutions for huge circuits that we often have in VLSI domain is not always possible. It is not always possible to apply optimal algorithms, because it may take years to give a solution. It may take even years, literally. So, we also have heuristic fast solutions, where the entire state space is obviously not searched, and hence the solutions are on most cases are suboptimal. However, the solutions often produced are quite good with respect to the best solution that we can get, and the advantage is that we often get the solution in very quick time. So, heuristic fast solutions are useful when the overhead for optimal solution is unacceptable, and good heuristics often produce near optimal solutions in many cases. The other approach is the stochastic solution approach. The stochastic solution approach, in this approach we start with an initial solution. So, a very crude heuristic fast solution could provide us this first randomly generated candidate solution, and from this solution we refine this solution through several iterations and moving through different areas of the state space and obtaining a solution. So, it will obviously again not always give an optimal solution, but in many cases the solutions are often acceptable and good. With this we come to the end of module 1 of lecture 3.